that's it. Put that in. Oh, oops. Just realized something, which is I forgot to copy over the agenda for today onto my flash drive. Oh, it's here. Okay, so it's 4 o'clock, so I'm going to get started. Oh, let me move this out of the camera. Okay, so today is Thursday, April 10th. Again, it's the second last class. There is class tomorrow. And what was I going to say before I got started? Nothing much I can think about. Oh, the other thing I want to mention, last class we talked about when my exam office hours are going to be. I believe we decided upon the Thursday, April 24th, the day before the exam, from 12 to 2 p.m. If I'm wrong with this, please correct me, but I believe that's what I remember from Tuesday's class. So again, if you have any questions for me that you want to ask in person before the exam, that's the only time I'm going to be on campus after tomorrow before the exam. Because I don't have anything to do next week on campus, and then the week after, again, I just have your exams. So that will be the day I'll be on campus that week. And it's definitely, if for whatever reason, if this time doesn't work for you and you want to come ask you questions a little bit before that, a little bit after, then just send me an email, and I can come a little bit earlier or stay a little bit later. But this is the time slot I will definitely be on campus before the exam. I also will have a practice exam. I was working on it before class today. It's not quite finished. I'll definitely have it finished before class tomorrow. So if you come to class tomorrow, you can get a copy of the practice exam to work on between now and then. And yeah. Oh yeah, and then the exam, sorry, the exam itself is Friday, April 25th, from 2 p.m. to 5 p.m. And I forget the room number for the exam. It's in this hallway. I think it's down that end of the hallway. It's like A30. I can't remember what the last digit is. Anyways. Actually, you know what? I'm just going to quickly look it up because I've got time. Oh, A301. Thank you. Oh, it is the very end of the hallway. Okay, A301. Thank you. Great. So just want to mention those things before we got started. And on to the agenda for today's class. Again, my goal for today's class is to finish up the last of the material, and then I might have time to start some review. There are a couple of Muddy's point cards I got last time that I want to go over. One of them is actually from the material that we did on Tuesday. The other one is from stuff that was earlier, so there will be a little bit of review happening during the Muddy's points section. Then I'm going to finish off the Chapter 9 material. Again, all the stuff from Chapter 9 here turns out to be really easy, which is one of the reasons we leave it to the end. Again, it's definitely a lot easier than the material that was in like Chapter 5, Chapter 6, Chapter 7, Chapter 8. So, and then I've got a group problem due at the end. Again, depending on how quickly I might get through this, I might throw in some more substantial review at the end as well. It'll just depend upon how the timing is going. And then definitely tomorrow's class is all going to be review. Okay. So, I'm going to first go over the muddiest points that I got in the cards from last time. So the first muddiest point card that one muddiest point card that I got talked about using quadrants when finding, sine inverse, cos inverse, and tan inverse functions. And so I've got sort of three examples I'm going to do to sort of talk about how those quadrants work when we're working with those guys. So, the first thing to mention, if I'm trying to find sine inverse of negative a half, what this is really saying is that sine theta is negative 1/2, right? And I'm trying to find the theta. I'm doing sine inverse of something that's really trying to solve the equation sine theta equals that thing. So we look on our unit circle. We're going to try to find a point which has, actually, I'm just going to, up in the corner before, draw those three special angles and their sines and cosines, just so we remember them. Again, the cosine is the x-coordinate, the sine is the y-coordinate. The cosines go 1, 2, 3 like that. Sines go 1, 2, 3 like that. We take the square root of everything and divide it all by 2. The smallest angle here is pi over 6. The middle one is pi over 4. And the largest is pi over 3. So if we want our sine to be negative 1/2, the first thing to mention is that the range of sine inverse is between negative pi over 2 and pi over 2. That's the range of sine inverse. So our angle has to be between this angle down here, negative pi over 2, and this angle up here, positive pi over 2. Here, if sine theta is negative, that means the y-coordinate is negative. So if we're between those two angles and the y-coordinate is negative, we're going to have to be in this quadrant somewhere, the fourth quadrant. It's the only way for the y-coordinate to be negative and for you to be between those two angles. So, we want our y-coordinate to be negative 1/2. Well, if the y-coordinate was positive 1/2, the angle would be pi over 6, right? That has a y-coordinate of positive 1/2. If we want it to be negative 1/2, rather than going up, we're going to have to go down. So the angle here is going to be negative pi over 6. So this point has a y-coordinate of negative 1/2. So here the answer is going to be negative pi over 6. Any questions about how I did that there? Again, I just want to sort of make sure that the logic that I'm explaining is clear. Because sometimes this is something people have difficulties with understanding why, it's negative pi over 6, it's not an angle over here, it's not 11 pi over 6. The reason it's not 11 pi over 6 is that would be too big, that would be bigger than pi over 2, even though it's also in the same quadrant. It's a positive angle in that quadrant rather than a negative angle in that quadrant, and that would make it too big. Okay, if we're going to do cos inverse of negative 1/2, the thing to remember is that the range of cosine is here. or the range of cos-inverse, sorry, is between 0 and pi. And if cosine is negative, cosine is the x-coordinate, so we want the x-coordinate to be negative, which means we're going to have to be in that quadrant. That's the only quadrant in this range where the x-coordinate is negative. So we want the x-coordinate, so if the x-coordinate was positive 1/2, we'd be here at pi over 3. That will have an x-coordinate of positive 1/2. If we want to find one which has an x-coordinate of negative 1/2, well, then this angle is going to have to be the same as this angle, right? It's going to have to be a mirror image of this, so that's pi over 3. So this angle is going to be, that angle would be pi, and we have to go backwards by pi over 3. So this angle is going to be pi minus pi over 3. That's 3 pi over 3 minus pi over 3, which is 2 pi over 3. So cos-inverse of negative 1/2 is 2 pi over 3. Any questions about how I did that one? Okay. If not, I'm going to move on to do the last one, which is a tan inverse one. So the first thing I'm going to do is I'm going to find the tangents of each of these guys. This top one, the tangent's the y over the x, it's going to be square root of 3. The middle one, the tangent's the y over the x, it's going to be 1. The bottom one, tangent's y over x, it's going to be 1 over square root of 3. Again, I should have made more space there so I could write out the tangents for each of those. So if we're trying to find tan inverse of negative 1, I'm trying to say that tan theta is negative 1. And if I want to find the range of tan inverse, again, this is one of the things in the formula sheets, it says that the range of tan inverse is from negative pi over 2 to pi over 2. So I've got to find something in here which is a tangent equal to negative 1. Well, if it was in this quadrant, the tangent would be positive, so it's got to be in this quadrant down here. So it's got to be somewhere in this quadrant. Tangent is positive 1 at the angle pi over 4. So if we went up by pi over 4, here the tangent is positive 1. So if we go down by pi over 4, here the tangent is going to be negative 1. So the angle here is going to be negative pi over 4. Any questions about how I did that one? Again, hopefully this answers a question that whoever it was wrote on the muddiest point card. The question wasn't written particularly clearly, so hopefully they're talking about how do you use quadrants when you're working with sine inverse, cos inverse, and tan inverse. So hopefully this answered that question. If not, again, feel free to put it on another muddiest point card. I can go over as much review of as much as people want to go over tomorrow. So. And the second thing I got on the muddiest point cards was a request to do a word problem involving systems of equations. So that's the word problem I'm going to do there. It's up on the board. Here we have a rancher who has 2,420 feet of fence to enclose a rectangular region that lies along a straight river. So here's a river. If you look at the textbook, you'll get an actual picture of this. If I was going to ask this particular one on the test, I would also give a picture of it. So we want to build a fence like this to enclose a rectangular region along a river. We're not going to use any fence along the river because the river is going to form a natural boundary. We're only to build 3 sides of fence. So the question is it possible to enclose that many square feet of land? Well, to figure that out, the first question, oh yeah, sorry. So maybe I should just write down the information that we're given. We're given an amount of fence. The amount of fence is 2,420. The area is 435,600. That's the area of the plot. Oops. So, the first question in a word problem like this, once you sort of draw a picture, summarize the information, is what are the unknowns? Can anyone tell me what the unknowns are in this situation? The first thing you mentioned about this particular question is badly phrased. It asks, it is not actually phrased the way I would phrase a question on the exam. Here it asks, is it possible to enclose this many square feet of land? The answer is actually yes. And for one of the ways you can answer that question yes without actually having to do any work, which is silly. I think it's, oh boy, I should have actually, no, I'm pretty sure it's possible, yeah. Yeah. No, it definitely is. The hard part of the question is figuring out how can we enclose this many square feet of land. And if I was going to ask this question on the exam, I would say, what are the dimensions of the plot in order to enclose this many square feet? So then what are the unknowns? I'm asking, what are the dimensions of the plot? Length and width, exactly. So the two unknowns here are the length of the plot, which is that side, and the width of the plot, which is that side. So now we've got the two unknowns, the length and the width, and we want to come up with two equations. And again, the equations will always come from the information that's been given to us. The amount of fence is 2,420. So we want to come up with an equation that gives you the amount of fence. Well, the amount of fence is going to be this side plus this side plus this side. So W plus L plus W has to equal 2,420. That's the first equation. The second equation is going to be the area. Well, the area of a rectangle is always the length times the width. And that has to be this number. 435,600. So now we want to take this equation and solve it. The first thing I'm going to do is I'm going to rearrange that first equation to solve for L. I'm going to leave the L on that side and move all the W's to the other side. So it'll be L is 2,420 minus 2W. And then I can plug that in to this equation. I will have 2,420 minus 2W times W equals 435,600. So this becomes 2,420W minus 2W squared equals 435,600. Just going to continue it over here. I'm going to move everything to the right-hand side, so I'll get 0 equals 2W squared minus 2,420W plus 435,600. Divide everything by 2, so it'll be W squared 1210. 56 divided by 2 is 28. Ooh. 721. There we go. That's still a really ugly situation. Oh, sorry, there's a W here. It's a quadratic polynomial now that we're trying to solve for W. And numbers are such that factoring is going to be really annoying, so instead I'm going to use quadratic formula. So W equals negative B plus or minus square root B squared minus 4AC all over 2A. Negative B is negative 1210. B squared is negative 1210 squared. 4AC is 4 times 1 times that big number, 217,800. All over 2A, which is 2 times 1. So 1210 plus or minus And this part I'm going to need a calculator for. If anyone's actually already calculated what's inside the square root there, I heard some people pull out the calculators a second ago. If anyone's done that already, this would be amazing. If not, I can do it. Okay, so it is great. 5,929,000. Square root of that. Square root 770. So if we do plus 770, so if we do 1210 plus 770 over 2, that gives you 1375. And if we do 1210 minus 770 divided by 2, that gives you 220. Okay, I'm going to close that door. Whatever's going on out there is distracting me at least. Great. Okay. So the two possible values for W are 1,375 and 220. So now that we have those two possible, oh yes.
Why is the first one 1,375?
Did I add it wrong? 1, 2, 1. I'm just trying this again. Maybe I made a calculation mistake. Did you get a different answer?
It's under 2,000. So I just figured it should be under.
You're right. 990. Thank you. That was a calculation error on my part. Thank you. Yeah. And then the last step is to take those two values for W and use them to find values for L. Right, so W could be this, W could be this. I have this formula. That says that L is 2,420 minus 2W. And that formula is what I'm going to use to find L in each of those situations. So the first one, I have 2,420 minus 2 times 990. So 2,420 minus 440. And the other one, L is going to be 2,420 minus 2 times 220. Which will give you 990. No, sorry. 2,420 minus 2,220 is 1,980. So, the field is either 990 by 440, or it's 220 by 1980. Either of those sets of dimensions will give you this area. This one makes a little bit, this one looks a little bit more reasonable to me than this one is. This one's very thin and very long. It's almost 10 times as long as it is wide, which would be, I think, a silly shape to make a field in. This looks like a more reasonable shape to me, but and they're still both possible. Any questions about this example? Okay. So I'm going to move on to continue in Chapter 9 where we left off. So, what we talked about last class, we talked about sequences. We talked about how do we use a formula for a sequence to have, find terms in the sequence. And the answer is just plug numbers into the formula in order to find terms. The next thing I'm going to be talking about sequences are these ideas of what are called recursively defined sequences. A recursively defined sequence, I think this is actually, in my opinion, this is actually the hardest thing in this entire chapter. It's not that, I don't think it's that hard, but yeah. A recursively defined sequence is a sequence where rather than having a formula it'll give you every term, you plug in 1 to get the first term, 2 to get the second, 3 to get the third. You actually have to know what the second term is to find the third one. You have to know what the third term is to find the fourth one. To know what the fourth one is to find the fifth one, etc. So that's what's going on here. So this is what's called a recursive definition. It says that one term is something times the term before it. How many people here have seen definitions like this before? Recursive definitions of sequences. I see a couple people. How many people have not seen anything like this at all before? Okay, so everyone, no one put up their hand for not having seen it at all. So hopefully that means you've all been familiar with it in one form or another. Again, the hardest part about this whole thing is being able to sort of understand this notation. And that's what I'm going to be talking about in the next slide. So a recursive definition is a rule for getting one term of a sequence from the term before it. So for example, one sequence I could talk about is one where each term is the square of the term before it. So maybe we start with 2. Then we square that, we get 4. Then we square that, we get 16. Then we square that, we get whatever 16 squared is. I think it's 256. We square that, we get something really big. I don't actually know what 256 squared is. About 40,000. Anyways, so that's one way of defining a sequence. It's saying each term comes from the term before it. If we want to write that out as a formula, the formula would look like this. AK plus 1 is the k plus first term. So if k was 2, AK would be the second term, AK plus 1 would be the third term. If k was 4, AK would be the fourth term, it would be A4. AK plus 1 would be A5. So it says you can get the third term from the second term by squaring it. You can get the fifth term from the fourth term by squaring it. You can get the 17th term from the 16th term by squaring it. That's the idea. That k plus 1 there signifies the next term, and the k signifies the k before. Yeah. If we want to actually start a sequence like this, if we want to actually figure out what the terms of a recursively defined sequence are, we need somewhere to get started. We need to know what the first term is before we can even get started. So for example, that one that I talked about that goes 2, 4, 6. So it starts with 2, and then you square it to get 4. So I'm not going to go 6. 4 squared gives you 16. Would look like this. We'd say, firstly, that the next term comes from the term before it by squaring it, and also that the first term is 2. So if we want to get the terms of the sequence, what we've got to do first is to find the second term. So first we plug in k equals 1. If k equals 1, this says that A2 equals A1 squared. Then we know that A1 is 2, and 2 squared gives you 4. If you want to find A3, you plug k equals 2 into this formula. This means A3 equals A2 squared. A3 equals A2 squared. A2 we know is 4. From the computation we did here, 4 squared gives you 16. If you want to find A4, you plug in k equals 3 into this formula. You get that A3 plus 1 is 4 equals A3 squared. A3 we already know is 16. 16 squared is 256. So basically, by plugging in one number for k after the other, we can find each term of the sequence one at a time. Any questions about how this idea of recursive definition works before I go on to do some examples? Okay, so example time. So the first example I'm going to do is this one here. Here we have a recursively defined sequence. A1 is 128, and AK plus 1 is a quarter times AK. That means we can get one term from the term before it by multiplying by a quarter. So A1 is 128. If we want to find A2, we've got to plug in k equals 1 into here. We get 1 plus 1 is 2 equals a quarter A1. A1 is 128, so we're having a quarter times 128, which turns out to give you 32. If you want to find A3, A3 is going to be a quarter A2. Again, that comes from this thing. If you plug in K equals 2 here, A2 plus 1 is 3 equals a quarter A2. A2 is 32. A quarter of 32 is 8. If we want to find A4, it's going to be a quarter A3. Again, we can get this idea by plugging in 3 into this formula. A3 is 8. We just computed that before. So we're doing a quarter times 8. A quarter of 8 is 2. And the last one, we want to find the first 5 terms. So we need to find A5 as well. And A5 is going to be a quarter of A4. It's going to be 1 quarter times 2. A4 was 2. A quarter of 2 turns out to be 1/2. So these are the first 5 terms of the sequence. It goes 128, then 32, then 8, then 2, then 1/2, and then it's going to keep on going from that point on. Any questions about this example?
Do we have to create that sequence of the answer? Just
No, if you write it like this, that's totally fine. I just want to show this to show sort of like that it looks like that's what a sequence usually looks like when you write it as a sequence, is a list of numbers. Yeah. Okay. One thing to mention is that there are recursive definitions which have a k in them as well as an ak. That means if we want to find the second term, we just take that formula and we plug in k equals 1. If we want to find the third term, we plug in k equals 2. If we want to find the fourth term, we plug in k equals 3. And if there's a k in that formula, k will become each of those things in turn. So this next one, example 3, we have A1 is 2, and AK plus 1 is AK all to the power of 1 over k. So if we want to find A2, we're plugging in k equals 1 into this formula, right? Plugging k equals 1, the k plus 1 there will become a 2. So we're finding A2. So we're trying to find A2, it'll be A1 to the 1 over 1. So it happens to be plugging k equals 1. A1 is 2, 1 over 1 is 1, 2 to the power of 1 is 2. If we want to find A3, we're plugging in k equals 2 to that formula. AK plus 1 will be A3, AK will be A2, 1 over k is going to be 1 over 2. A2 there is 2. 2 to the 1/2 is also known as the square root of 2. So if we're trying to find A4, again, using this formula, we're plugging in k equals 3. That means we're going to have A3 to the 1/3. A3 is square root of 2. So we have square root of 2 to the 1/3, which is the cube root of the square root of 2. And if we want to find A5, again, it finds the first 5 terms, it leads up to A5. If we plug in k equals 4 to that formula, we'll have A4 to the power 1 over 4. A4 is the cube root of the square root of 2. And if we're putting it to the 1 over 4 power, that means we're doing the 4th root of it. So A5 is going to be the 4th root of the cube root of the square root of 2. Again, it's a really ugly written number like that. There are some things we can do to simplify it. Don't worry about trying to simplify things like that. Just write it out the ugly way. The key thing I'm trying to test here is not your ability to simplify square roots, but your ability to actually use this definition. Any questions about example 3 before we move on? Okay. The last thing I'm going to mention in this recursively defined sequences section is the idea of what's called second-order recursion. Second-order recursion means rather than just using one term before it to find the next term, you need to use two terms before it to find the next term. So here I could find a 2 just using a 1. I could find a 3 just using a 2. I could find a 4 just using a 3. If I needed like a 1 and a 2 to find a 3, I needed a 2 and a 3 to find a 4 and a 5 to find a 6, etc., then we're doing what's called second-order equation, or second-order recursion. In a second-order recursion equation, we have both an AK and an AK minus 1 in the formula, something like this. This says that AK plus 1 is 3 times AK minus 2 times AK minus 1. It's saying that the next term is going to be 3 times the term before it minus 2 times the term before that one. And if you've got second-order recursion, you need two terms to start off with. You need to know A1 and A2 to find A3. You can't find A2 just from A1 because there's no A0. So in second-order recursion, you need to have two things to start off with as well as a recursion formula. So, example 4 here. We have a 1, which is 3. We have a 2, which is 1. And we have this formula. AK plus 1 is 3AK minus 2AK minus 1. So that's the formula we've got. And they want us to find the next three terms. So we know what the first term is. We know what the second term is. The next thing we need to find is the third term. Now, if we're finding a 3, that means we're plugging in 2 for k into that formula. Because if we're finding a 3 is a 2 plus 1. 2 plus 1 will give you 3. So we're going to have 3 times a 2, putting in 2 for k, minus 2 times a k minus 1 is then 1. Because k is 2, k minus 1 is 1. So a3 is 3 times a2 minus 2 times a1. a2 is 1. a1 is 3. 3 times 1 minus 2 times 3 turns out to give you negative 3. If we want to find a 4, we're plugging in k equals 3 into that formula up there. We plug in k equals 3, we'll have 3 times a3 minus 2 times a2. a3 we just found is negative 3. a2 we just found is 1. 3 times negative 3 is negative 9. Negative 9 minus 2 is negative 11. And then if we want to find a 5, we plug in 4 into that formula. We'll have a 5 equals 3 times a 4 minus 2 times a 3. a 4 is negative 11. a 3 is negative 3. 3 times negative 11 is negative 33. Negative 2 times negative 3 is positive 6. Negative 33 plus 6 is negative 27. And again, this is the next three terms. We found a 3, a 4, and a 5. Those are the next three terms they asked us to find. Any questions about example 4 here? Okay. Okay. So what I'm going to talk about next is the idea of what's called a geometric sequence. How many people here remember geometric sequences from high school? How many people here have studied them but totally forgot about them? How many people here have never studied them at all? Anyone? Great. Okay. The key thing, and I don't know if you remember this from high school, for those who took it before, the key thing about geometric sequences is to know the formulas. If you know the formulas, all the questions about them turn out to be really straightforward. The formulas will be on your formula sheet for the geometric sequences. I realized I didn't put them on the version of the formula sheet I used last week for the quiz, because I totally forgot that there were formulas from this section. So they are going to be on, I'm going to make a new version of the formula sheet, which I'll hand out tomorrow with the practice exam. I'll also put out the new version of the formula sheet on the course webpage in the practice test folder, if you're looking for it, to make sure you know what those formulas are. Okay. So geometric sequences are sequences where you multiply by the same number to get from one term to the next. So this is a geometric sequence, 1, 3, 9, 27, 81, because each time we're multiplying by 3. 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. This one's a geometric sequence because each time we're multiplying by negative 0.1. 1 times negative 0.1 is negative 0.1, negative 0.1 times negative 0.1 is 0.01, etc. This is a geometric sequence because each time we're multiplying by 3 over 2. 4 times 3 over 2 is 6, 6 times 3 over 2 is 9, 9 times 3 over 2 is 27 over 2, etc. To define a geometric sequence, what we need to know is we need to know what do we start with, what the first term is. So we need to know what's called A1. A1 is just the symbol for the first term. And what is the number that we're multiplying by each time? The number we're multiplying by each time is called R. We're trying to figure out what R is in a geometric sequence. We just take the second term divided by the first term. A2 over A1 will always give you what the ratio is, what you're multiplying by each time. So once we know what the first term is, once we know what R is, we can find any term in the sequence, AN, by starting from the first term and multiplying by R a certain number of times. If we want to find a second term, we've got to multiply by R once. If we want to find a third term, we've got to multiply by twice. So the number of times you've got to multiply by R is n minus 1. That's where this formula comes from. It says the nth term is the first term times R to the power of n minus 1. That's sort of the main geometric sequence formula, and that will show up on your formula sheet. Any questions about what a geometric sequence is or that geometric sequence formula before I go on to examples using it? Okay. So, the main thing we're going to use this formula for is to find terms of a geometric sequence. So if I give you like the first 3 terms, I say, what is the 10th term? Using that formula is going to be the easiest way to do so. So here, I have a geometric sequence. I've given you 4 terms. I want you to find the nth term. If I ask you to find the nth term, that means I want you to find a formula for AN, find a formula for the sequence. And if I want you to find the 8th term, well, that means I want you to find A8. So, this is example 5. So the first thing I mentioned, the first term is 2, right? You can see what the first term is. If we want to find the R, want to find what we multiply by each time, just take the second term over the first term. We're multiplying by 3 each time. Right, this is times 3, times 3, times 3. So the formula for the nth term is going to be this. A1 times R to the n minus 1. Again, that's just that formula from that previous slide, with the A1 being 2 plugged in and the 3 plugged in. This is the formula for this sequence. 2 times 3 to the n minus 1. If we want to find the 8th term, all we've got to do is plug in 8. So 8 minus 1 is 7, so this is 2 times 3 to the 7th. And if we do that, 2 times 3 to the 7th, we get 4,374. Did I? Yep. Yep. Okay. Any questions about example 5 here? Great. Again, these questions should be really easy. Where they get a little bit confusing is something like example 6. Example 6 is a sequence which has variables in it. This is something that exists. They're useful for studying. In fact, actually, you may see some of these in Calculus 2, sequences with variables in them. Something called a power series, which you may see in Calculus 2 eventually. And there also could be geometric sequences. Here, again, we want to do the same thing. We want to find the nth term and the 5th term. Well, here the first term, A1, is 1. If we want to figure out what R is, we've just got to take the second term over the first term. The second term is negative x over 3. The first term is 1. We divide something by 1, it never changes it. So the R is just negative x over 3. So if we want to find a formula for AN, all we're going to do is we're going to do 1 times R to the n minus 1. That's the formula for AN. And then it wants you to find the 5th term. So if we want to find a 5, we've got to do it like this. 1 times negative x over 3, all to the 5th power. And if we do something like this to the 5th power, first the negative number to an odd power will still be negative.
Isn't it 4? And minus
1. Oh, yes. 5 minus 1, which is negative x over 3 all to the 4th. Yes, so it's being put to an even power, so it's going to be positive. X to the 4th is just x to the 4th. 3 to the 4th is 81. So the 5th term here is x to the 4th over 81. Let me write that 8 a little bit better. It looks like a P almost. There we go. X to the 4th over 81. That's the 5th term. So again, there are sequences which have x's in them are totally legit. And you can study them using exactly the same geometric series sequence formula. Any questions before I move on? Okay. Please make sure this is still recording. Great. Okay. Wait a second. This isn't, okay. Anyways, the section numbering on this is wrong. This is 9.1.3. So the last thing I'm going to talk about in this course is what happens when you add sequences together. You do what is called a summation. So a summation is this symbol that looks like this thing. Here it's a Greek letter sigma. In fact, it's a capital sigma. Lowercase sigma looks completely different. Yeah. Anyways, it's called summation. How many people remember how to use this symbol and do something like this? People have seen it. How many people have seen this thing before and have done it before but forget how to do it? As most people. How many people have never seen this symbol at all before? Okay. So the main thing I'm going to explain at this place is what the symbol means. What does that big capital sigma letter mean? Well, the idea is that sometimes you want to add together the terms of a sequence, like this. 1 plus 4 plus 9 plus 16 plus 25. Right? If we're trying to add together numbers which follow a pattern, sometimes it's annoying to have to write out the entire thing. For example, if I kept this pattern going, plus 36 plus 49 plus 64 plus 100 plus 121, if I had like 10 terms I was adding together, it would be a really annoying thing to write out. So mathematicians invented this thing that's called sigma notation. And sigma notation has 3 different elements. This thing after the sigma tells you what the formula is for the sequence you're adding together. If you look at these numbers up here that you're adding together, each of those numbers is a square. So that's why it's a k squared there. It's saying that the sequence you're adding together is a sequence of squares. The number at the bottom says where you start. You start with what happens when k equals 1, which means you can get this first term by plugging in 1 into the k squared formula. The top tells you where you stop. And here we're stopping at 5. That means the last term should be what you get when you plug in 5 into the k-squared formula. And that's why it's 25. So if you ever set sigma, that means you're adding a number of terms together. You can find each of those terms by plugging in different values into the formula after sigma. So you can always find the first term by plugging in whatever's on the bottom. So plug in k equals 1. That'll give you the first term. When you find the second term, plug in the next number after 1, which is 2. Second term is 2 squared, which is 4. Find the third one, you plug in 3, 9. Find the fourth one, you plug in 4, 16. Find the fifth one, you plug in 5, gives you 25. And again, gives us a 5 on the top. That means that's where you stop. So the number below tells you where the first value you plug in. The number up top tells you the last value you plug in when you're doing sigma notation. Any questions about what those different things in the sigma notation represent before we move on to examples? Great. Okay, so I'm going to go on to some examples. So, example 7 is the first one. So here we're going from k equals 0 to 4, and we're doing k minus 1 times k minus 3. So the first thing I'm going to mention is basically just sort of writing out what we're going to be doing. Well, first we're going to do k equals 0, then we're going to do k equals 1, then we're going to do k equals 2, k equals 3, and k equals 4. Right? We go from k equals 0 to 4. When k equals 0, we have 0 minus 1 times 0 minus 3. When k equals 1, we have 1 minus 1 times 1 minus 3. When k equals 2, I'm just going to make more space. When k equals 2, we have 2 minus 1 times 2 minus 3. When k equals 3, we have 3 minus 1 times 3 minus 3. And when k equals 4, we have 4 minus 1 times 4 minus 3. So we've got negative 1 times negative 3 here, which is positive 3. 1 minus 1 is 0. 1 minus 3 is negative 2. That gives you 0. 2 minus 1 is 2. 2 minus 1 is 1. 2 minus 3 is negative 1. 1 times negative 1 is negative 1. 3 minus 1 is 2. 3 minus 3 is 0. 4 minus 1 is 3. 4 minus 3 is 1. So 3 plus 0 plus negative 1 plus 0 plus 3. What does that give you? 5. So the idea is you just got to figure out what are the numbers between here and here, plug each of those numbers in. Yes, Kat? This is not the number of terms. This is the number you stop at. It's not the number of terms. And technically, this is how I would like to write it. This is not the mathematical convention, but I would usually write k equals 0 to k equals 4. Just to tell you exactly, this is telling you what the last value of k is, it's not telling you the number of terms. Yeah. Yes. It is, most of the time, if you start at k equals 1, it is the number of terms. And that's the thing that, like, yeah. But it really is telling you the number you stop at. Yeah. So example 8. Sorry, maybe I should, here. I'll erase example 6, and I'll sort of start example 8 over here. But I'm going to need to. Oh, yes, Dan?
Good question. Is there any notation for if you have like some of every third term in sequence? Like,
No. Well, yes, but you will not ever learn that in this course. I don't even remember what it is. For every second term, I think they do this or something like that. There was a, oh, no. Yeah, anyways. Actually, now I remember. If you're doing it, no. That's how you do it if you're doing every third term. You actually write the words, K is a multiple of 3. That's how you do it if you're doing every third term. You actually just use, yeah, there is no special symbol for it. You actually just write it out in words. Yeah. You are not going to have to deal with that in this course. And I was just trying to remember, wait, I had seen that before, what do they actually do? And yeah, they just, yeah. So, K equals 0 to 4, 3 times 2 to the K. So here, again, first I'm going to plug in K equals 0. I'm not going to have space right over there. I'm going to have to erase this. I'm looking at it and I'm like, I don't have a choice. Okay, so we plug in K equals 0. We'll have 3 times 2 to the 0. We plug in K equals 1. We have 3 times 2 to the 1. We plug in K equals 2. We have 3 times 2 to the 2. We plug in K equals 3. We have 3 times 2 to the 3. And we plug in K equals 4. We have 3 times 2 to the 4. 2 to the 0 is 1. 1 times 3 is 3. 2 to the 1 is 2. 2 times 3 is 6. 2 squared is 4. 4 times 3 is 12. 2 cubed is 8. 8 times 3 is 24. 2 to the 4th is 16. 16 times 3 is 48. 34 plus... I'm just going to use a calculator. It's going to be faster. 3 plus 6 plus 12 plus 20 plus 24 plus 48. 93. So there we go. That's what we get from example 8 there. Any questions about that? Okay. Last example of this I'm going to do is example 9. The one thing to mention is that it is very possible for there to be a variable in the formula which is not the one that you're plugging in. So here, what? There's totally a mistake there. Let me just check the textbook. I think it's supposed to be 8 to 11, not 8. There's no way it's going to be 8 to 1. Yeah. So let me just check the text. I think it was 8. Oh! No, I know what happened. The 4 went in the wrong place. Yes. Yes, it's this. 8 to 14. 3 times to the K minus 7 plus 2J squared. So the key thing to mention in this sum is that because it's K that goes from 8 to 14 here, we're plugging in numbers for K. We are not plugging in numbers for J. The J will just stay as a J when we're plugging things in. So it'll be, I'm going to start it here, 3 to the 8 minus 7 plus 2J squared plus 3 to the 9 minus 7 plus 2J squared plus 3 to the 10 minus 7 plus 2J squared plus 3 to the 11 minus 7 plus 2J squared plus 3 to the 12 minus 7 plus 2J squared plus 3 to the 13 minus 7 plus 2J squared plus 3 to the 14 minus 7 plus 2J squared. So again, I had to write it on 2 lines to get that whole thing in, but that is one sum. So 3 to the 8 minus 7, 8 minus 7 is 1, that's just 3. 3 to the 9 minus 7 is 3 to the 2, which is 9. 3 to the 10 minus 7 is 3 to the 3, which is 27. 3 to the 11 minus 7 is 3 to the 4, which is 81. 3 to the 12 minus 7 is 3 to the 5, which is 243. 3 to the 13 minus 7 is 3 to the 6, which is 729. And I don't have 3 to the 8 memorized. Wherever I put that calculator. No, 3 to the 14 minus 3 to the 7. 2,189. So that's all the powers of 3. Then we've got the 2j squared, 2j squared, 2j squared, 2j squared, 2j squared, 2j squared, 2j squared. We've got 1, 2, 3, 4, 5, 6, 7 of them. If we combine them all together as like terms, we're going to have a 14j squared there. And if we do 3 plus 9 plus 27 plus 81 plus 243 plus 729 plus 2189, it gives you 3281. Ah, plus 14j squared. So 3281 plus 14j squared is the answer here. Again, the key thing is you can use summation notation even if there's variables in there that aren't the variables you're plugging in. Okay. Last thing I'm going to cover in this entire course, in terms of new material, is geometric series. Getting closely related to geometric sequences. The main difference is in a sequence, you're just talking about the terms. In a series, you're talking about adding the terms together. So here, what we've done so far is we've talked about a number of different series. We talked about what that sigma notation means and what it means to add together and how you can add together terms by doing each one. In 9.3.3, we're going to be adding together terms using formulas. This sum here, 1 plus a half plus a quarter plus an eighth plus a 16th, that's an example of a geometric series because each time we multiply by the same thing. Multiply by half, multiply by half, multiply by half, etc. So the key thing that we're going to use here is we're going to use formulas to find those sorts of sums. The first formula is for the formula what I call a partial sum. Partial sum means we're adding together some of the terms of a sequence. Again, a sequence always has an infinite number of terms, even if we're only looking at the first few. So partial sums means we're only adding together some of those infinite number of terms. Oh, sorry. The first thing I'm going to talk about before I start finding sums is how to write these things in summation notation. So the first thing to mention, we want to write it in summation notation, is we need to find a formula for the terms. So example 10 here, I have 2 minus 4 plus 8 minus 16 plus 32 minus 64. Right? The key thing to mention here, the first term is 2, and each time we're multiplying by negative 2. From here to here we multiply by negative 2. Here to here we multiply by negative 2. Here to here we multiply by negative 2, etc. The key thing, what was I going to say about this, is that means that we can get a formula for the sequence. And that formula for the sequence is exactly what you put after the summation symbol. Right? Getting a formula for the sequence tells you what you have to put after the summation symbol. And again, this formula is just the an equals a1 times r to the n. N minus 1. K minus 1. Sorry. Remembering the formula wrong. Anyways. And then we want to sort of symbolize where do we start and where do we end. Well, we end at 2. 2 is the first term of the sequence. So we start at k equals 1. We end at 64. 64 is the 1, 2, 3, 4, 5, 6th term of the sequence. So we end at 6. Again, as long as we start at this first term, this is the same thing as the number of terms. If we started somewhere other than the first term, it wouldn't be. But because here it is, we started with the first term, a1. There are 6 terms, we do stop at 6. Any questions about how I did example 10 there? Next thing to mention is that we can figure out what the sum of this sequence is. We can add them together using a formula. This formula is the formula for the sum of a geometric sequence, or what's called the partial sum of a geometric sequence, called Sn. And you know what the first term is, you know what the r is, you know the number of terms you're adding together. you can just pull out this formula. So if I want to figure out what this thing is, I could pull out that formula, plug in A1 is 2, R is -2, N is 6. Plug those all into the formula, I would get an answer. So, example 11. I tell you that I want to find the sum of a geometric sequence. A1 is 17 over 16, R is 3, and N is 8. Well, I can just use this formula. The A1 is going to be 17 over 16. R is going to be 3. N is going to be 8. There we go. There's the formula. Three to the 8 is 6561. 1 minus 3 is -2. If you do this on your calculator, it'll give you -3485. Sorry, I'm not going to show the work. I'm just going to pull up the calculator. That's what we get at the sum of the sequence. So again, this formula, also going to be on your formula sheet, is useful whenever we're adding together a certain number of terms in a geometric sequence. Again, we could apply this formula to example 10 if we wanted to. Because here we know what A1 is, we know what R is, we know what N is. Any questions before I move to the last slide? Okay, last slide of this course is what's called a geometric series. A geometric series, I just realized that's the tab I left open on my laptop that was making these beeps. A geometric series is what happens when we're adding together all the terms in a sequence. So partial sums is when you only add together 6 of them. A series means you're adding together an infinite number of terms. And series are something that's going to come up again in Calculus 2. When you get there, that's sort of the main thing that you will see again in calculus. So for a geometric series, for an infinite sum, there is also a formula. The formula looks like this: A1 over 1 minus R. The key thing to mention is we can only add together an infinite number of things if those things get smaller and smaller. We can't take 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 and expect to get a non-infinite result. But if we do like 1 plus a half plus a quarter plus an eighth plus a 16th, we're actually adding together smaller and smaller things. So what will happen to those things as we add together is that the sum is going to increase by smaller and smaller amounts, and we will actually get a finite result. We will get an actual, if we actually do that, 1 plus a half plus an eighth plus a 16th plus a 32nd, etc., we actually get 2 as the answer. As we add more and more things, we get closer and closer to 2. So this is what this is saying here. Absolute value of R is less than 1. It's saying we can only find an infinite sum if we're multiplying by a number that's smaller than 1, whose absolute value is smaller than 1. So last example, example 12 here. Here we have the series 1 minus 0.1 plus 0.001 minus 0.01, 001, etc. So as the geometric series, the first term is 1. The R is always the second term over the first term, which gives you negative 0.1. If we take the absolute value of R, we take the absolute value of negative 0.1, which is positive 0.1. That is less than 1. So because the absolute value of R is less than 1, we can use that formula. A1 is 1. 1 minus R is negative 0.1. That gives you 1. 1 plus 0.1 is 1.1. as a fraction, this is 10 over 11. So if you add this infinite number of things together, the answer you actually get is 10 over 11. And one of the annoying things about this course, I don't have the theory to sort of talk about what it means to add together an infinite number of things. For any of you who are interested in what happens when you add together an infinite number of things, and oh boy, if any of you have ever looked up Zeno's paradoxes, they're basically very closely related to this. Zeno was a Greek philosopher back in the day, and he basically believed that physics was impossible, that physics didn't exist, and that physicists were just making things up. That like their motion didn't exist, speed didn't exist, time didn't exist. And the reason for it is because he talked about like you have to add together an infinite number of things to do speed calculations, and that doesn't exist. Anyways, so if anyone's interested in that sort of stuff, Zeno's paradox is a great thing to look up. And so for the last 12 minutes of class, we're going to do our group problem. I'm not going to have time to do any more review today. Tomorrow I'll go into do review of the whole course. And for today, that is the group problem. Find the sum, k equals 1 to 9, of -5 all to the k. The hint here is that that is a geometric series, or sequence. It's a geometric sequence, sorry. So you can actually find its sum using one of those formulas I showed you. So if you can work on that for another 6 minutes, and then I'll go over the solution to it, and then you can go. Oh, I should hand out some money support cards. Again, if you have anything at all about the course that's confusing you that you want to go over tomorrow, feel free to put it on a money support card, and I will go over. Again, I will also do a quick summary of like what we've covered in the course, as well as any other review that people specifically want to do tomorrow. So tomorrow will be a review class. I will also be handing out the practice exams. I will also try to remember to bring chocolate for everyone tomorrow. That's always my like end of year celebration thing. Yeah. What is this? Blank piece of paper. Here. Yes. Yeah. Yeah. Exactly. So that 50 is going to be. And then because it's right in the slip. Yeah. Yeah. Exactly. Yeah. And then for this part, can I join these options? That has to be 40 degrees. This has to be. Oh yeah, it will be 40 degrees, but they don't tell you what it's going to be. This is 90 degrees. Yeah, it just helps. Well, yeah, this angle is 90 degrees. Yeah. Just like when I asked you if this would be 90 degrees. It would be 90 degrees. Yes, it would be 90 degrees. So that angle's not right. Oh, there's not a triangle. There's another angle here. That's the thing. It's not a triangle what you've drawn. Well, if you meet this line, this line, it would be a triangle. Well, this would be a triangle. Yeah, that's what I'm saying. This is not a triangle. Yeah, but you can use this triangle with the right angle to find the side. I'm also not convinced that these angles are over 80. Or maybe they are. Actually, because of these two. Oh, that was a coincidence then. That's a total coincidence. Yeah. Okay. I thought it was wrong. Yeah. Yeah. Okay. I did not even intend to. I never even drew. Wait, which was? Yeah, I never even sort of drew the lesser triangle from the other leg when I was doing it. Yeah. Yeah. Okay. But yes, that is confusing. And that's yeah. Yeah, that this angle is not that angle between this line and the line that so this 50 degrees is between this line and this vertical line. The vertical line goes past the 10 and goes to the 10. Well, no, it's not the same because from this 50 degrees, that angle is not 50 degrees. What I was trying to say is that so the point is that
You did it right.
Wait, that was. I'll get that right.
I don't know if I'm doing it right. That's what I did. All over the paper.
Sorry, anyone else have any other questions? Yes. I think so. I will believe, yeah. There you go.
Why is the first one 1?
Because that's the starting.
Go for it, yeah. Yeah, order does not matter. I did the table, but yeah. No. Anyone else have any questions for me?
Yeah, you might. I always thought. The 1. Right, okay, yeah, you're right.
Okay. So I'm going to go over the solution for this problem. And then folks can go. So here, this is the sum we're adding together. The first thing I'm going to do is I'm going to write out the first couple terms of this. So if I plug in k equals 1, I'll get this. If I plug in k equals 2, I'll get this. Negative square root of 5 to the 1 is negative square root of 5. This thing squared is just 5. So my A1 is, the first term is negative square root of 5. The R is always the second term over the first term. 5 over negative square root of 5. And 5 divided by square root of 5 is just square root of 5, so this will be negative the square root of 5. Will be the thing you're multiplying by each time. Again, because we're starting at the k equals 1, the number up top is the number of terms. So we can just use the formula for Sn. Oh, I'm going to turn that off. Anyways, A1 is negative square root of 5. R is negative square root of 5. And the bottom, we have that. So it gives you negative square root of 5. 1 minus square root of 5 to the 9th is going to be it's going to give you that, 625 square root of 5. Basically, square root of 5 times 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 square root of 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. These two give you 5. These two give you 5. 5, 5. 5 times 5 is 25. 5 times 5 is 25. 25 times 25 is 625. and this square root of 5 is left. And a negative number to the 9th power is going to be negative. Negative, negative gives you positive. And that's what you get. And that's the answer that I got. Again, other people got different answers because there are other things that are equivalent to that but not the same. But yeah. And I found that easier than computing each of these things separately and then adding them up. I used to actually use the geometric series formula. Any questions about this? Yes? Another question? It's not about this. Okay, great. So if there's no questions about this, I'm going to, class is done, but you can ask other questions and I'll come around.